packed with people, all forced to watch a complex event unfold through a single narrow window. If you pull just one person aside and ask them to describe what happened, they'll give you a highly specific story, but that story is limited by their singular angle. In machine learning, a standard decision tree operates like that isolated observer. It partitions the training data into smaller and smaller subsets to reach a conclusion, but its logic is tied to the specific path it took through the information. Because of the way a tree is built, as a strict hierarchy of splits, the slightest error or shift in the data at the very top node propagates downward. That single mistake shifts the branches, changing every outcome that follows. Relying on this rigid, isolated perspective results in a model with high variance. Instead of finding the true underlying pattern in the data, the tree often memorizes random noise, making it unstable. This instability becomes a serious liability when these algorithms operate in high-stakes environments. We currently use these models to diagnose medical conditions, approve loan applications, and assess risk in the criminal justice system. Consider the COMPASS system, a risk assessment tool used by courts to predict the likelihood of an offender committing another crime. It serves as a case study of what happens when a vulnerable algorithm ingests historical data filled with human prejudice. Minority communities have historically faced higher rates of policing and arrests. When a single decision tree looks at that skewed data, its tendency to overfit causes it to draw the wrong conclusion. It learns to equate a person's race with a higher risk of crime. We cannot entrust life-altering decisions to a fragile single point of failure. To build an algorithm that makes reliable, equitable decisions, we need an architectural shift. The solution is known as a random forest. Instead of relying on one volatile decision tree, we plant hundreds of them, creating an ensemble that works together to form a consensus. But there is a mathematical trap. Given the exact same training data, they become perfectly correlated, building identical logic pathways and making the exact same mistakes. This crowd acts like a single, massive individual. Rather than neutralizing biases, this approach merely amplifies them. For a crowd to actually possess wisdom, we have to force the individual decision-makers to be independent from one another. The first mechanism we use to break that correlation is called bootstrap aggregating, or bagging. Bagging creates diversity by changing what each tree sees. We feed each tree a different, randomized sample of the master dataset. Certain data points are deliberately left behind. By keeping this out-of-bag sample hidden during training, the system can later test its own accuracy. By preventing any single tree from looking at the entire picture, we ensure that they each develop a unique, independent perspective on the problem. To push this independence even further, the random forest applies a second mechanism, feature randomness. Even with unique data points, trees might still fixate on dominant variables. So, at every single branch, the tree is statistically blinded to certain features. It is forced to evaluate its next move based only on a random, limited subset of available options. When we introduce new data, these uniquely trained, constrained trees evaluate the problem simultaneously. Each one reaches its own conclusion and casts a vote on the final outcome. Because the models are completely decorrelated, their individual flaws point in different directions. The random errors from one tree are counteracted by the differing opinions of the others, effectively canceling each other out in the aggregate. Stability and accuracy emerge when the fewest democratizes the flaws of hundreds of weak algorithms, leaving behind a robust consensus. The foundational rule of this ensemble is that the combined verdict of the forest is far sturdier than any single tree could ever be. Which naturally leads to a question. If 100 trees provide a solid consensus, wouldn't 10,000 trees yield perfect accuracy? This chart maps the algorithm's error rate against the number of trees in the forest. You can see a sharp drop initially, but the model quickly hits a statistical ceiling. Once the trees are sufficiently decorrelated, adding thousands more simply wastes computing power. The error rate flatlines because the underlying bias has been reduced as much as mathematically possible. The wisdom of the crowd has a mathematical limit. An ensemble can optimize the information it possesses, but it cannot invent details that aren't there. A random forest is still vulnerable to a different type of failure, omitted variable bias. If human creators exclude a critical piece of context from the training data, The algorithm has no way to factor it into the consensus. In the absence of that crucial variable, the diverse trees don't argue or disagree. Instead, the entire forest will confidently and uniformly vote for a biased or incorrect answer. Returning to our room full of observers, no matter how rigorously they vote on the information they have, they can never account for the information that was hidden from them. While a random forest addresses the structural instability of the machine, it is defenseless against the blind spots of the humans who planted it.